Okay, so this is where we got to. The ones that are logs, which don't have powers, and the ones which are brackets, which do have powers. And in both cases, we are looking for something here or something here, which looks a bit like what you get when you differentiate that or that. Okay, so let's look at ones where, which one is it? Which one is it? So let's try a couple of examples. So let's do this first. So how on earth am I going to integrate that? Well, can I rewrite it to make it look a bit like one of the others? Well, it's obviously not a log one because it's not a fraction. But as is nearly always the case, the secret here is to rewrite it like that. And I can't help noticing that when I differentiate that, I don't get that, but I get something that looks a bit like that. So this is another example of one of these. So start off by asking, what do I get when I differentiate something? But I'm going to leave you to work out what is the thing you need to differentiate. Think about what we did here, and you do the same thing with that example. So I'm hoping you increase the power by 1. Less obvious maybe, but just like we did here, we realised that that is the answer to a bracket differentiation where the power was 4. Because the integration reduces the power by 1, so similarly I had to increase the power here by 1. Multiply by the power, reduce the power by 1, multiply by what you get when you differentiate the brackets. 1.5 times 12 is 18. So that is almost what I've got there. So if it was that being integrated, that would be my answer. As it is, it's 1/6 of that. So it's 1/6 of that is my answer. So not obviously one of the bracket ones, but rewriting it is sort of unlocks that one. It's just the powers are a bit fiddly. What about this example? Surely this is a log one, isn't it? I mean, log one where this looks a bit like what you get when you differentiate this, and in this case, looks exactly like what you get when you differentiate that. But no, we've got the power in there. So this isn't a log one. This doesn't come from a log. So let's do what we did there. Let's rewrite it like that. And let's see if we can work out what we need to differentiate, and in particular, I mean, it's going to be this to the power of something, but what's that power going to be? Think about what we did when it was to the power of 3 in that previous example, or here when it was to the power of a half. What did we differentiate? So what are you going to differentiate in this case, and then have a look at what you need to tweak. So hopefully you realised that we needed to increase the power by 1, which meant -2, not -4. So I increase the power by 1. So when I differentiate that, multiply by the power, reduce the power by 1, multiply by what you get when you differentiate the brackets, so we get that. I haven't got that, I've got that, which is -1/2 times it. So it's -1/2 times that. I have a feeling I forgot plus C in the one I've just rubbed off there, so don't forget your plus C. And so what about this one? Well, hopefully you can see that that one is a log one. There's no power. There's no power in the denominator. So this is just like the ones we did at the beginning of Friday's lesson. This looks like what you get when you differentiate this. In fact, it is identical. So the secret will come from differentiating that and then seeing if there's any tweaking needed to get back to that one.
possible to speak to you about an incident, please?
1 over that multiplied by what you get when you differentiate that, which is 4x. Bingo. So this is the answer with the added little modulus signs and the added plus c. So spotting the difference between those two types is bad enough that you've got to spot the two types in the first place, but I forget if we got onto this exercise on Friday, but let's just pick out a couple to practice. So George, could you pick out an example of a question that would be a log answer?
Oh, goodness gracious me.
No, don't want the answer, I just want, which one of those would you use the log technique, the one we've just used there? Yeah, A is a log one, isn't it? There's no power in the denominator, so that's definitely an ln one. James, could you pick out another one where we'd use the log technique?
B.
Yeah, B again. No power there, and I know when I differentiate e to the 2x, I get 2e to the 2x, which looks a bit like that. So those are log ones. Hopefully you can see that this is a bracket one. So it's going to have to be rewritten as x times x squared minus plus 4 to the power of minus 3. So just try and get those three. I'd love to say let's spend the whole lesson on all of this, but we don't have the time. So the first two I differentiated ln of the denominator. You get 1 over that denominator multiplied by what you get when you differentiate the denominator. And then I just tweaked it. So it was half in both cases. This one's much harder, although because if you tried to do the log thing, you wouldn't get something that could be tweaked to. I guess if you use the wrong approach, you'll hopefully realise it's wrong. Yeah, you've got to rewrite it because there's a power in the denominator, that's the power of minus 3, and so you want to differentiate something with the power 1 bigger, because the first thing I'm going to do after multiplying by the power is reduce the power by 1. And then multiply by what you get when you differentiate the brackets, which is 2x. So that's going to give me minus 4x. I've just got 1x, so that's minus a quarter. And it's minus a quarter of that. Which, of course, I could write as minus 1 over 4, that's the fraction, it's got a 1 on the top and a 4 on the bottom, and this is the same as that squared, isn't it? So you could write it like that. Doesn't have to be written like that. Oh, plus C. Didn't you write plus C? Okay, let's move on back to integration. Okay. Before I give us a title, here's what we're going to integrate next. In fact, I'm already regretting writing it there, so I'm going to rewrite it here. Now, this isn't the first time we've seen the integral of one thing multiplied by another. We've just seen some examples of that, but this doesn't fall into either of the two categories, because certainly when you differentiate this, you don't get just x. But this is still a product, isn't it? And we know that we have, when we differentiate, a product rule that allows us to differentiate things like that. We call one u and one v, and we put it into our windows. Well, what we're going to learn to do today, or start to learn to do today, is integrate products. So we're going to be dealing with expressions that involve one thing multiplied by another, but that don't fall into either of those two categories that we've just been discussing. Now, I would love to say, okay, let's at this point spend half an hour going through the formal derivation of this rule, but it's not on the syllabus, and the rule itself is on the formula sheet. So if you are intrigued as to how you get from the product rule for differentiating, here's the product rule. For some reason in this book they've decided to write it the other way round, but we know it's that times that added to that times that. That's the product rule. You can actually rearrange it to get what we call, down here, what we call the integration by parts rule, which is on the formula sheet. So if you are inquisitive, that's on page 307. I encourage you to look at it, but maybe leave it till after the mocks. However, the rule as it stands is if you want to integrate something that's a product, you don't put the two things here and here. The rearrangement says one of them has to go here. One of them has to be dv by dx. So to use this integration by parts rule, we start by putting our two things here and here. And again, this is on the formula sheet, so you don't need to remember this. It's on page 7 of the formula sheet. If we do that, the answer to the integral is u times v, this times this, take away the integral, because we need to do some integration, of v, this, multiplied by du by dx, this. And that's with respect to x, so that's just reminding us that x is our variable. And this is called integration by parts, but it's a product rule rearrangement. So let's go to my example. Okay, if you want to know why it works, then like I said, page 307. I'm choosing not to do that at the moment. So my example was, so I need, in order to use this rule, to put one of those two things here and one of those two things here. That's what the integration by parts formula tells us. And actually, there's no fixed way as to which way around it goes. It's not automatically the first thing goes here and the second thing goes here. We know when you multiply two things together, order isn't important. So I could put cos x there and x there, or x there and cos x there. Generally, there's an easy way to do it. And I think as you get better at this, you'll realise the easy way to do it. In this case, the easy way to do it by far is this. And that's because to complete the windows, normally when we use the product rule with differentiating, we put the two things here and we differentiate them both. Now, with integration by parts, because of this proof here, which I'm not going to go through, we have to differentiate that and integrate that to complete the windows. So when I differentiate x, I get 1. That's why it's much easier to put the x there than there, because if you integrate x, you get x squared divided by 2, which is just fiddly. When I integrate cos, well, when I differentiate, sine becomes cos, so when I integrate, cos becomes sine. There's a plus c there, but all I'm going to do is at the end of my answer, just write up 1 plus c. We know that when we integrate, there could be constants popping up all over the place. We tend just to write a plus c at the end. So I'm just going to use the rule. The rule says that the answer to this is u times v, so that's those two multiplied together, and whichever order makes sense to write them, seems to look nice to write it like that. Take away that times that, so that's v times du by dx. Well, that's nice and easy because that's sine x times 1, so that's sine x. And I can integrate sine x because I know that sine becomes cos, cos becomes minus sine becomes minus cos. So when I integrate sine, I get minus cos, but I've already got a minus here. So actually I end up with x sine x plus cos x plus c. So there you go. I've saved c to the end. Integration by parts questions are normally quite easy to spot. It's a fairly obvious one thing multiplied by another thing, and sometimes they even say use integration by parts to integrate. So there's that extra little bit of help in there as well. Page 7 of the formula sheet is where you find this example. Sorry, that rule. So nothing to remember there. Just need to remember how to use it. And it's probably best to do a few more examples to get used to it. So here's a classic parts question. It's obviously an integration by parts because it's a product and there's no relationship between these two things. So it's not one of those other forms that we've been talking about over these last few lessons. So I'm going to start by loading up my Windows. And I said that it doesn't matter which way round you do it, but sometimes one way is easier. Well, that's not always true. It would be tempting to put the x squared there, because when I differentiate it, I get 2x, which is much simpler than putting it there and getting x cubed divided by 3, increase the power, divide by the new power. However, I don't know how to integrate ln x. We haven't done it. It's not on the formula sheet. So I can't put it there. I can put it here, because I know what you get when you I can't integrate ln x, I can differentiate ln x, so I'll just get 1 over x. That's nice and easy. That means the x squared has to go there. And when I integrate that, when I integrate x squared, increase the power by 1, divide by the new power, I get x cubed over 3, which looks nasty, but remember what we're about to do. We're about to plug it into a formula which involves multiplying those two together, so it's not as bad as it seems. Do you want to have a go and see if you can plug that into that formula? Now we've completed the Windows. So we get that. I mean, it doesn't look pretty, but that's because this is a really complicated function, and we're not expecting the answer to integrating it to be straightforward. So I integrated x squared, differentiated ln x, uv minus the integral of those two multiplied together, which simplified down to x squared over 3. I increased the power to get x cubed, divided by the new power. Well, I'd already divided by 3, so that's dividing by 9 altogether. And then at the very end, I popped a little plus c. You know those Russian dolls where you open one up and there's another identical one inside? Well, let's have a look at another example, which, because this is relatively straightforward, you begin to ask yourself, how do they make it more complicated? Well, here's an example of one that makes it a little bit more complicated. Firstly, e to the x in an integration by parts question is a punch the air type thing, because e to the x, we know when we differentiate it, we get e to the x. So it doesn't change. Wherever you can, it's like a freebie, you can put it in either one. So put it where the other one is best put. So I'm definitely going to put my x squared up here, because that differentiates to 2x. That's much simpler than integrating it. And e to the x that just becomes e to the x when you integrate it. So see if you can plug that into the formula and see what you notice. I'm just not saying anything, not going to give any game away, but I'm going to do another little set of windows down here.
Okay, well, he's just being. In his view, he's done nothing, therefore he shouldn't go.
Yeah, that's what happens.
So do you see how you get another product within this parts question? So to integrate this, I'm going to have to use integration by parts again. It's parts within parts.
Integration parts.
There we go, integration by parts squared, yeah. So I still think I'm going to be okay doing that, because e to the x is like that freebie. So I'm going to put a big old set of brackets here and switch to blue and pretend this is like a whole new question, and I'm going to write my answer there, and then I'm going to sort of roll it all together with the final answer. Sorry, excuse me. Okay, see if you can factorise your final answer, your final answer. So it ends up quite nicely, because I know the integral of e to the x is e to the x and 2 passes through unchanged, so I just end up with that. But I've just got to be careful, because remember, this is within the answer to the original question, and there's a minus there. So I've got x squared e to the x minus 2x e to the x minus plus 2e to the x. So actually you can factorise that and you get a quadratic in the bracket. I mean, that's largely irrelevant. And then, let's see. Integration by parts tends to be quite popular I mean, popular is the wrong word, but they are questions that are often done quite well because they're a little easier to spot, although there are some more complicated things. So after,